You might change what's brought into the vault. You might decide that certain data sets aren't critical anymore, or they've moved. And being able to use this GUI, especially on the right side here with things like policies, to update that is all very easy and straightforward. And then you can see here too, the recovery tab. We've automated a lot of the recovery processes. So if there is an attack, you know what to do, and you can do it at least partially on an automated basis to speed your recovery and make it as efficient as possible. A couple things that we've learned about cyber recovery and resilience that are important to a solution that's going to be effective. And again, tying this back to the whole spectrum of threat actors and the tools and capabilities that they have. So we think about this on a couple of different levels. And you can see on the slide here, good, better, best. And of course, you want to get further up as you assess the risks and the importance of your data in your environment. So good capabilities are things like making the data immutable. Some people will call that WORM, write once, read many. There's a standard out there called 17A4F that people use to kind of take the place of WORM. But essentially what we're doing is we're making that data harder for a bad actor to delete. So if they get into our backup environment, our infrastructure, we've locked the data. And note that I did say harder or more difficult to delete. Data that's locked really isn't immutable. There are ways to attack the data. There are clock attacks. There are insider attacks. So it's a good control that you want to add to a solution, but it's not a solution in and of itself. Then as we move into better, how do we improve our positioning there? Well, one thing is let's protect from insiders. So having those capabilities to separate the systems that an insider can't even get access if they know where everything is, putting physical controls on rooms and locks, separating duties so that different people can do different things. Those are all components of a solution that are important too. But as we get into best, this is really where we separate from everybody. And the key there is having that air gap, that operational air gap that separates the system from any bad actors that don't actually have physical access. And that's almost every case. So doing that alone is a huge step up from the good and better. I'd mentioned sheltered harbor before. There's not a lot of standards in this area. So when you look to how do we benchmark our capabilities or our solution, Sheltered Harbor is a financial services initiative that looks at a lot of these things and has some recommendations on it. We're the only group that's working with them in their technology solution provider program, in their alliance program. So that's a really great data point. And then the last piece is analytics. How do we know that what we put into the vault is good data? And then can we use that data when we recover? You think about some of these attacks, you don't know that an attack is, for example, a NotPetya attack, which happened a few years ago, until later. All you know is that your systems have gone down, your data's locked up. Having analytics for your vault data can tell you immediately what data is good and what data is bad. So you might be able to use some of the data that didn't get impacted. You might know that some of your data from today is bad. And think back to my sync, copy, lock, analyze process. You may have a copy of an application, for example, from the day prior that's good, and you can reuse that versus having to go back and set things back up. So all that information leverages into the process of enabling your recovery to be more efficient and more effective. This is kind of my specialty area. I know puts some people to sleep, but what's happening in the regulatory environment, what's happening in the legal environment, and we're tracking along with those things. And in fact, in many cases, we're helping to drive those. So in the US, we tend to have more industry-specific requirements, and healthcare and financial services really lead the way. They're talking about, as you can see from the FFIEC, an air-gapped data architecture. Our FBI, which is a group that we get to spend time with here, is talking about backups and ensuring they're not connected to networks that they're backing up. So you think about those backups being attacked from my earlier slide, that's really what they're referencing there. Outside of the states, the protections tend to be more broadly structured. So they're not going to be sectoral in an industry, but things like the GDPR, which protects personal data, actually has some cybersecurity requirements to it. And just fascinating to me, again, GDPR has been out for a few years, that they mention what I talked about before, confidentiality, integrity, and availability of the data, not just the confidentiality, which is the theft, but if you're going to have that data, you've got a responsibility to make sure that you can use it and that it's secure and available. So this is the path that we're working down. And when you think about how these all coalesce, it's an air-gapped copy of data that's protected in the data vault. That's the best way to meet these requirements as they become more structured, more strict, and more important in the coming years. So when you look at the competitive differentiators, and this is similar to the slide that I showed you before, I think it's important to understand what else is out there and where it may fall short. So in many cases, what we see from others in this space is just taking a backup and hardening that backup. And as I said before, things like immutability, which you can see across the top row here, it's important, it's useful, but it's not a solution. It's just an extra control that's going to make that data a little bit harder for a bad actor to reach. We're operating across all of these different capabilities, and they're all very important. So as you look at other solutions, really understand what they do, what they don't do, and where the gaps are going to be. They're going to protect typically against the, I mentioned before, garden variety bad actor, and not against insiders, not against more sophisticated threat actors, and not against things that are cyber warfare like NotPetya that we saw a few years ago. So be very careful and be very informed on all these capabilities and determining what's necessary for you to really keep a safe copy of data. I talked a little bit about the analytics and want to talk a little bit more. So how do you know that data in the vault is good? And that's what we do with our CyberSense capabilities. So think about the sync, copy, lock, analyze. We're bringing data in to the vault. We don't care if it's good or bad data. It's not going to run in the vault. So if there's malware in our backup that we're bringing into the vault, or there's dormant malware, it doesn't run. It can't impact our vault because we're keeping it in this backup format. But we want to know, is the data good? So what we do with our analytics is we take that data once it's in and locked into the vault, and we scan it. We don't have to restore it. We can read through the backup format, and then we're going to make some observations, some statistics on all this data. We're going to go at an operating system metadata level. Did the size of the file change? Does it have an extension that might indicate it's been corrupted? We're going to look at the application metadata. So think about a database having an actual structure to it, that if that whole structure is gone, then that data is corrupt. But then we're also going to look at the full content. So we're going to measure things like Shannon entropy that might tell us that data has started to get encrypted. We've got chunking and similarity algorithms that will help us compare files day over day. We're going to take all that information and feed it to a machine learning algorithm that's going to help us understand whether that data has been corrupted. So no, we're not looking for malware. We're looking for evidence that the data is not useful. We repeat, we do that day over day. We have all these comparisons, and then we've got all that information available to us. So we'll send out from the vault a simple report card. Data looks good, data is suspicious. And then if you go into the vault, you can look all the way down to the file level to every single observation that can get you all the information you need to help determine root cause and help figure out how you're going to recover. Really important. I mentioned before the critical data. So as we work across industries, every industry has different focus areas. You can see a few here. I spend a good amount of time in the financial services area. So banks and credit unions looking at core banking. Some are looking at trading platforms. In the legal community, document management is really important. You know, all data is going to be important at certain levels, but what we're really looking to protect in the vault are those critical data sets that without you really do not have a business. You can't operate at all. So get those into the vault and make sure that they're protected. I've mentioned Sheltered Harbor a few times. I think it's a really good organization for people to look at for best practices. Shelteredharbor.org is the site. If you're in the U.S. banking and financial services industry, you can be an actual participant. And I think it's a good evaluation to make. It helps protect the U.S. financial system. If you're not a potential participant, the ideas that they have, and you can see here on the right, for example, how they require a data vault, the characteristics that are necessary to protect data are useful. So the unchangeability, the separation of the data, make sure that it's accessible. All those components add up, and there's more technical requirements there that are really useful. We're looking forward to winding up our last step of our endorsement process this month, which is August 2020, and continuing to work with the organization and their participants out there. So just kind of wrapping up here, why Dell Technologies for cyber recovery? I mentioned before kind of some of the specifics here. The air gap is hugely significant. Just making data immutable or locking it is a good step, but it's not enough. All of our experience in this space, really good. 5 years, we know what we're doing. We've made changes to the product over time to reflect some of the new techniques. And then the analytics in the vault, going full content. All of those things really add up to a very robust solution. We've got a lot of other materials out there on our website, videos, case studies, white papers. Recommend that to you also. So I want to thank you very much for your time. Look forward to the opportunity to maybe speak with some of you in the future, and be safe and take care. Thank you very much.
Hello, everyone. My name is David Santos. I'm an NSX engineer. And today we're going to talk about VIO, VMware Integrated OpenStack, and NSX. How a VIO is an easy button for OpenStack deployment, also with the NSX providing the network. So here we're going to talk about the architecture, the VIO architecture. In the middle, we have VIO, and it will be consumed by Horizon. That's the project that provides the user interface, the UI interface. We're going to consume our infrastructure as a service. And in the back, we have the VIO products. We have Nova for computing, and in the VMworld, the Nova will be provided by vCenter and ESXi. Here we have a benefit of using VMware as our Nova project, because vCenter will be the single endpoint for all the Nova workloads, and also have native VMware features like DRS and vSphere H8 that helps with the availability of the environment. And we have Cinder as the block storage. In the VMworld, Cinder will be provided as our data store. So every time that we use a data store, it will be used as a Cinder block storage. Neutron will be provided by NSX. Like Nova, NSX has a benefit that will be the single endpoint to deploy networking, like layer 2 switches, routers, load balance, and firewalls. We also have Glance. Glance is the image project for OpenStack, and in the case of VMware, the Glance will be the VM templates that will be used and that will be consumed in VIO. So before we start, we need to deploy some objects in NSX. In this case, we need to deploy a T0 router, and also we need to exchange the routes between T0 and a physical router using BGP. This way, everything that we deploy in VIO will be automatically distributed to the physical infrastructure. So After that, we're gonna have our first step, that is to create a local network. In this case, we're gonna create a local network called local one, and we're gonna connect two VMs in that network, web 01 and web 02. So here I have our network topology. I'm gonna create the local one network, create a subnet for that network that's called local one subnet, and also provide the IP address for that network. And it will automatically use the first IP as the default gateway when you create that. And now we're gonna connect our web 01 and web 02 to that network. Web 01 already connected, and now we're gonna connect the web 02. And now I have already layer 2 connectivity between those VMs, and I'm gonna connect to the web 01. It asks for changing password because the first time that I connect to that. And now I'm gonna ping to the web 02, and you can see here that the ping is working. So the second part is to create the routing network. So to do that, we're gonna create a router in VIO in the NSX, and like under the hood, what will be done is NSX will be configured to create a new T1 gateway, a new T1 router, and also we're gonna use the T1 router to provide connectivity between the local one network that has just been created, and to local 2 network where we're gonna have our other VM that's at 01. So we are in the routers tab. We're gonna create a new router here called VIO router. And then we're gonna access that router and go to interface, add a new interface, select the network that will be connected, and it automatically will use the first IP as the IP for that router. And that will be our default gateway. You can check in the topology that will have our router connect to local 1 and local 2. Now I'm gonna connect the Apple 1 to that network. Apple 1 is already connected to the local 2, and it gets its IP address automatically using the HCP. And if I do a little ping here to my web 02 or to my Apple 2, the ping works successfully. The third step is the external network. So the external network is kind of an IP pool that will be used as a floating IP or like external load balance IP. It doesn't create a real network. It creates a pool that will be consumed either as a floating IP or a load balance IP. But it doesn't create anything. In this case, that external network will be used by this T0 to provide NAT or to provide or to deliver those IPs to our objects that will be published externally. So as it's an external network, we need to do that in the VIO admin level. So this way we can share that network with among all the projects that we need. So I need to go to the admin level, go to network, and here I'm gonna create a new external network. I'm gonna call that network external, select the project, this way, in this case will be admin, And it's a local network, but I select here shared and external. I include here the subnet name that will be used as our pool name, and also the IP address that will be delivered to that pool. It doesn't have a gateway. It doesn't have a gateway now, neither DHCP. We cannot create DHCP. We cannot set DHCP rules in the external network. And here we can check that our external network has already been configured. The fourth step is the floating IP. So the floating IP will be done by connecting that T1 to our T0. Actually, we're going to connect that T1 to the external network. That what is showing. That's what is shown on the VIO console, and it actually is will distribute the floating IPs that we assign to the VMs here. So when you create that, it will create a source NAT rule to all those VMs communicate with an external, with an external network using a source NAT IP, and also to the ingress traffic, the traffic that comes from the external, like the physical network. We need to provide a floating IP to those workloads. This way, we don't need to redistribute or to share the internal networks with like a physical network. It helps a lot when you have like bubble environments, or when you have a multi-tenant environment and you have IP overlapping. This way you can have multiple identical networks with identical subnets, sharing only the floating IP as a common network. So this way we're gonna go to routes. It has to be done. It has to be done in the project level, and here in the VIO router, I select my external network as my source, my way to the to external world. And here I can see that all the networks can communicate externally, and I'm gonna create a floating IP. So I have 50 floating IPs available. I'm gonna allocate one to my project and associate that floating IP to my WebO1. After associate that, I can successfully do an SSH to that VM. And here I will log in and try to do a little ping to my app VM, and the ping will work as it worked before. The fifth step is the load balancing. So we're going to create a load balance that will be placed in the T1, and our pool members will be WebO1 and WebO2. So I also need a floating IP pool to do that. That IP pool will be associated to our load balance later. I go to neutral load balancer, create a new load balancer. I can select here a name for that load balance, select which subnet will be connected, the load balancing protocol, that in this case will be HTTP, also the port that will be used, and the method in this case will be round robin. Here I select the pool members that will be WebO1 and WebO2. Also can select the port if it's another port, the monitor, I can select like get to a specific URL or an object, and it's really simple to create a load balancer. After that, we need to associate that load balancer to my floating IP. And once that's associated, we can connect it to our network, to our application that's running in that network using the floating IP. You can see that's load balancing across Web01 and Web02. The last step is the sixth and last step is the security group. So security group will be delivered by the NSX DFW. So in this case, we're going to create a new security group called allow HTTP and block everything else. It will allow external, like ingress traffic to HTTP, like to a web application, like Apache or any Nginx. And I will associate that security group to my Web02. That my Web02 is in the full security group now. If I try to ping my Web02, it works. And if once I change my security group to allow HTTP and block all and remove the default, I can check here that the ping is no longer working. So I can see the packet drops here. And that's all I have today. Thank you very much for watching. See you next time.
Hello and welcome to this talk. I'm David Espejo. I'm based out in Colombia, South America, and I've been part of the vBrownBag community for quite some years. So I really appreciate the chance to share these topics at VMworld 2020 Tech Talks. So let's get started. In this session, we will talk about a little bit on distributed systems theory and why it is important for us in IT, right? So first of all, theory, right? That sounds really academic, and it's really academic. So first of all, why? Why to bring this topic from textbooks, from academia to IT? Why it is important? Well, first reason, it's because distributed systems are all around us in the everyday systems, products, protocols that we use and consume every day. They are all around us. And in my experience, this academic topic is not open for the interpretation of a specific vendor. It's a concise, exact, precise topic that when it's clear for us, and that is the main goal of this session, to try to bring light on how these topics can be found or can be traced to most of the systems, protocols, and products we use on the day-to-day operations of an IT environment. So examples of distributed systems will be, for example, DNS, the distributed naming service, network file systems, some network protocols like BGP or VXLAN, and even Netflix. It's a planetary scale distributed system that happens to provide the streaming services to end users, right? So they are all among us. So now if that is pretty much clear on the why of the importance of this topic, what is a distributed system? For most of these definitions, I will reference the textbook by Professor Tannenbaum, who is very famous. He wrote several textbooks that are used throughout computer science schools throughout the world. And he provided some definitions for this topic. So first of all, a distributed system, it's a collection of autonomous computing elements that appears to its user as a single system, right? So there's a lot there to unfold. I will try to unfold a little bit this definition. Examples of distributed systems that operate like the textbook definition are, for example, a vSphere cluster. You have several nodes. Let's say a node in this context can be a hardware device or a software process. There will be several nodes that appears to its user as a single system. You log into vCenter, you see a cluster. A cluster itself, it's a form of or an implementation of a distributed system. For example, NSX has most of these services are distributed by nature. So it's a collection. There are several components. And one of the principles is that each component could act or could operate independently from each other. But in the practice, they will need to communicate, right? You have several components, but they will need to communicate to achieve a common goal. So the next base feature is the single coherent system. Its users are not aware of the distribution of processes, services throughout many nodes and many systems. No, they will see or they will operate this as a single system. This is not the same as having a single view, right? If you are thinking about the infamous single pane of glass, I will dive a little deep on this in the next slide. It's not the same. It's just the coherency here comes by providing the user an experience in the system that behaves exactly the way the users expect it to behave, no matter where it's deployed, no matter how it's consumed. It will respond to user requests exactly how they expect it to answer or to respond, right? And for me, this has a lot to do in the trade-off between complexity and abstractions. You know, most of the promises that technology do today is providing simplicity, right? Eliminating complexity, and complexity cannot be eliminated. So the formal definition for complexity is shown there in the presentation. There was another professor called Herbert Simon. He provided a formal definition for a complex system that happens to be one made up of a large number of parts that interact in a non-simple way. So it's very similar to a distributed system. We can say that a distributed system, it's always complex, right? But simplicity, it's not just removing parts, because the system needs all of its parts. It's just, hiding the diverse components, hiding them from the users, and make the system appear as a single coherent system, right? So that is the abstraction, the most realistic goal with a complex system. Well, so let's dive a little deep on the base features. First of all, a collection of autonomous elements. If you have several elements, they will need a way to communicate between each other, to exchange messages between them. And also, if you have different independent components, nodes, or processes, more likely each process will have its own notion of time. There is nothing like a global clock for a distributed system, so you will need a way to provide time coordination. And also, if you have several members or several nodes to form the system, you will need a way to manage membership. You can have an open group when whatever node can be part of the group and can send messages to all the members of the group, or you can have a closed group. And if you have a closed group, you will need a way to authenticate a protocol to authenticate nodes, to accept nodes into a cluster, and once accepted, to provide authorization on or trust on which part of the groups it can communicate to. So the technical or academic definition for this problem is admission control. So it sounds very familiar to a vSphere HA cluster, which happens to have an admission control mechanism. So examples of these requirements or these features for distributed systems implemented in the day-to-day components we use in IT, it's, for example, AMQP or RabbitMQ, a protocol, a messaging protocol used by some VMware products. Or NTP, the Network Time Protocol, and a way to provide time coordination for a distributed system. Active Directory, for example, an example of authentication protocol to accept or deny requests to join a group. Single socket layer, TLS, etc. Different ways to provide trust for this collection of independent entities. And the single coherent system, as I was referring previously, it's not the same as a single system view. It's not the single pane of glass. That is a fair goal, but it is harder to achieve than just to say it. So it's the trade-off between appearance versus expected behavior. And the coherency here has more to do with expected behavior than with appearance, right? So the overall goal is to hide the complexity, but the most important goal is that the system behave exactly like its users have designed it to behave. Right? When you have different components, you will need a way to provide services for these different components. That is being called middleware. And middleware provides at least 3 functions to a distributed system. First of all, communication. It will provide mechanisms to communicate components of the distributed systems. It will provide transactions, a way to manage transactions, because most of the times an application relies on different services that are distributed along many nodes or components of the system. So the scalable way to manage that is by using transactions. And finally, reliability, a way to handle partial failures. If you have a system made up of different nodes, you will have to face the reality. A part of the system will eventually fail. So how to hide the partial failures of the system from the users? You will need a way to handle rapidly or have a way to tolerate failures. So you will see this in operation in an HA or high availability event in a vSphere cluster. It's just a way to restart automatically VMs in another node. That is a way to hide or to manage partial failures of the systems for the user. So examples of middleware services are, for example, RPC, which is a highly used protocol or communication protocol used in Windows environments, for example. The microservices design pattern of today's applications relies on communication between components provided by an API, which happens to be kind of a middleware. And also serverless. Serverless work only with transactions, probably atomic transactions, but those are transactions provided by this, let's say, middleware layer that are necessary for a distributed system. So in summary, that's it. In my opinion, when you gain more knowledge or at least study a little bit this distributed systems topic, you will get a better idea on how to design an IT environment, and also it will set your expectations at the right level on how it operates. So I appreciate the chance, and I hope you like this talk. Thank you for watching.
Welcome to this vBrownBag session deploying SQL Server 2019 big data clusters on Kubernetes with Ansible. Today we're going to explore one of the many different ways to deploy a Kubernetes cluster with the end goal of deploying a Kubernetes application, in this case Microsoft SQL Server 2019 big data clusters. My name is Doug Bernhardt. I'm a senior principal engineer with Dell Technologies. I've been at Dell now for a little over 8 years, and I've been working with SQL Server for over 25 years. Storage is obviously a very critical component of a big data or database environment. So now my primary focus is SQL Server and storage integration. While I've managed to hack out what I needed in VMware to get the job done and learned a fair amount about Kubernetes, Ansible, and Linux along the way, my primary background is SQL Server. My journey to Kubernetes and Linux and tools such as Ansible was one of necessity. Since my background is primarily SQL Server, my main goal was to deploy this new application, knowing that I needed a Kubernetes environment, and it was prior to the release of vSphere 7 or even the beta. Therefore, as part of my research and trying to get a Kubernetes environment up and running, I found the method that we're going to cover to be very well suited to my needs. Over the coming days, you'll surely hear a lot about forward-looking concepts and what's new in vSphere 7. This session is not about that. We're going to walk through a basic deployment of Kubernetes that's on a very simple environment of good old ESXi and vCenter. Also, keep in mind that there are literally over 100 different distributions to Kubernetes, as well as various different deployment models. This is a deployment of open source Kubernetes, or what is often referred to as vanilla Kubernetes. To perform the deployment, we're going to use basic VM templates and Ansible open source playbooks. Finally, we will deploy a big data application, Microsoft SQL Server 2019 big data clusters. There are various use cases for this deployment method. Maybe you're not ready to go to 7.0 just yet, or perhaps you want a similar deployment process and tools for bare metal, cloud, and VMs. This deployment method is similar to what you might use to deploy on bare metal with a few virtualization twists. We've got a lot of ground to cover, and this session is a whirlwind tour. If you don't get everything, no worries. I have a link to a paper at the end of the session that covers everything in detail. SQL Server Big Data Clusters is a big data and AI platform that deploys a data lake in a box, as I like to call it, on Kubernetes by running a single deployment command. As part of that deployment, application components, including SQL Server instances, Spark, HDFS, and tools such as Grafana and Kibana are all deployed as Kubernetes pods in a single namespace. Since we're working with a data application and containers are ephemeral in nature, the deployment will dynamically provision persistent volumes, somewhere in the range of 28 to 50 or 60, depending on how large you wish to scale the cluster. Because we're working with big data, some or all of these volumes could be several terabytes in size. Knowing Kubernetes is required, I want to use vanilla Kubernetes. I quickly realized I needed to figure out a way to deploy, and this was prior to the latest offerings from VMware. My research quickly led me to different solutions using Ansible. For those of you not familiar with Ansible, a little background. Ansible allows for agentless automation. So you install Ansible, and it allows scripts or collections of scripts organized as playbooks to be run against one or more targets. One of the great things about Ansible is that the scripts are designed to be rerun without harm, if needed, to achieve a desired state. If the target is already in the desired state, then the scripts will simply find nothing to do. There are various modules available for all sorts of operating systems, cloud environments, and hardware platforms, and a very rich library of existing playbooks and samples that can be leveraged. In my case, I was able to find a couple of open source playbooks to accomplish what I needed, customize the parameters for my environment, and execute these playbooks for deployment into the Kubernetes environment. So let's take a look at that now. Here are the high-level steps for this process. First, you'll need to install Ansible if you've not already done so. Next, create a template Linux VM to be used as the deployment source for our multi-node cluster. In this example, I'm using RHEL as my OS. The important thing here is to find an OS supported by kubespray, which most Linux distributions are, and then to use an OS that is supported by the application, in this case, SQL Server Big Data Clusters. Also, in the template VM, you may wish to pre-pull packages that will be downloaded, install tools, etc. Next, Kubernetes will be installed using kubespray. Kubespray is a really cool tool because it not only automates the deployment process, but supports a lot of different options such as networking types, cloud providers for storage, Linux distributions and is therefore really customizable by just changing the config parameters. Finally, we can deploy our application, in this case, SQL Server 2019 Big Data Clusters. Now that we've covered the steps, let's quickly walk through a demo of this entire process. The first thing that needs to be done is to build a template to use when creating the cluster VMs. This will be used as a consistent starting point for all of the VMs in the Kubernetes cluster. It's a process that most VMware users are familiar with. You create a VM in the state that it will be the starting point for your VMs in the cluster. Then you shut it down and convert it to a template. Some tips for setting up the VM template. If you take away one thing from this session, it should be this. When working with Kubernetes and vSphere, make sure to set the disk enable UUID property to true. The persistent storage driver uses this to identify storage resources, and if this is not set, persistent storage provisioning will not work, and the errors may not be clear as to why. When you're finished with the template configuration, after you shut down the VM, remove the network adapter. The deployment scripts will add it back and configure it, but they may not work properly with an existing network adapter. Since setting the disk UUID property is so important, let's quickly run through how to do that. Select a VM, in this case the one to be used as a template, and go to Edit Settings, VM Options, and then click the Advanced section and choose Edit Configuration. Here, choose Add Configuration Params and enter disk.enable UUID for the name, true for the value, and click OK. Once the template is ready to go, you can deploy the VMs using the VMware Guest Ansible module. First, you'll need to install Ansible if you don't already have it somewhere. It's agentless, so you just install it on a machine that has access to everything you wish to automate. And as I mentioned earlier, Ansible has several modules that know how to communicate with various infrastructure components. Using this module, you can start with an existing playbook or write your own. I happen to find one to start with on GitHub that you can pull down as a starting point and simply customize the parameters, so that's what I'm using here. The way this playbook is written, I have two configuration files, one with the common settings and one with the settings for each VM. In this case, I'm using a file called answerfile.yaml to specify the VMware environment settings, as well as some common VM settings. As you can see, there's a section for my vSphere environment specified, as well as all of the common guest settings. In another file, I specify the settings for each VM I want to deploy. Ansible has a concept of an inventory file, which is a list of items to configure. In this example, the inventory file is called VMs to deploy. In here, I'm specifying that I'm going to build 5 nodes, 1 master and 4 workers, giving each its own name, IP, and notes. Now, running the command Ansible playbook and passing in the inventory file and the playbook name, this will deploy the VMs. Each VM was deployed as a task. The result is listed in the play recap section, where we see that each VM has a status of OK and changed equal to 1, showing that the deployment changes were applied. A properly written Ansible playbook can be rerun without harm. So here you can see where I reran the script and it just simply came back with everything OK and changes equal 0, so no changes were applied. Now that the VMs are deployed, the Kubernetes cluster can be deployed on top. In this example, I'm using kubespray, which you can read more about on the Kubernetes website, and pull the source from the GitHub link listed here as well, but it's the same idea. Pull down a set of playbooks, customize for the environment, and run. The biggest difference here is that since kubespray offers several different options, there are a lot more parameters that can be specified, but it's still fairly straightforward. First, we need to build the inventory file. This is what the inventory file looks like. We're specifying the names of the Kubernetes nodes as well as the connection information. So this file needs to be updated with the info for all the nodes of the cluster. Next, you need to configure the persistent storage, which in this case we're using vSphere data stores. This is all done in the all.yaml file, which you can see here in the center of this file is the cloud provider and is set to vSphere, as well as the vSphere credentials and parameters. From here, kubespray will deploy and configure the vSphere cloud provider. Note that this example uses the older in-tree cloud provider. vSphere CSI support was added about 3 months ago to kubespray, so you may want to look at using that instead. but for now, this method works just fine. Depending on what other Kubernetes features you want to modify, such as the overlay network, Kubernetes version, etc., these values can be specified in the other configuration files as well. Just look at the documentation to find the location of the feature that you wish to change. Finally, we run the Ansible playbook command above, and it begins deploying the Kubernetes environment. This is a rather lengthy deployment because it does a ton of work. In my environment of 5 nodes, this takes around 15 to 20 minutes for this process to execute. Once the deployment is complete, the Ansible play recap shows all of the changes that were applied. The final step before deploying the application is to create a Kubernetes storage class. This references a storage provider installed with the cluster, and it points to the data store we wish to use as well as the file system. Here's an example of the storage class definition, and it's created using the kubectl command. Now that the cluster configuration is complete,